Welcome back. Today we'll be talking about variable separable differential equations. Variable separable differential equations. Suppose you have dy over dx, first order dy over dx equals a function of x and y. We don't know those functions now. We are saying they are functions of x and functions of y. Now, if this function of x and y can be separated, if this function of x and y can be separated to these forms, let's say h of x over h of f of y, or let me say b of y, if they can be separated into two other functions such that one of the function is a function of x only and the other is a function of y only, it is called variable separable. If you can separate them to have two different functions such that one is a function of x only and the other is a function of y only, it is called a variable separable differential equation. So it could be of this form. Either the function of x is at the top, then the function of y is at the bottom, or the two functions are multiplying each other, or the function of y is at the top, or the function of x is at the bottom. So these are the three possible forms of observing to get your differential equation. Since your differential equation is a function of x and y, and if you can separate this function of x and y into two other functions, where one of the functions is a function of x only and the other is a function of y only, it is called variable separable. So when you have the first scenario, case 1, this is case 1, case 2, and this is case 3. So for the first case, we have dy over dx is equals to h of x all over b of y. Now, this function of y should go to this differential coefficient y, and this function of x should come to this differential coefficient x. So when I cross multiply, I will have b of y times dy equals to h of x times dx. Now, because this is a function of x and we have differential x, we can integrate both sides. Now, when you integrate both sides, you will obtain the solution to the differential equation. So this is case 2, where we have dy over dx is equal to h of x times b of y. Now this h of x should come to this differential x, and this b of y should come to this differential y. So we have dy over b of y is equals to h of x times d of x. Now after separating it like this, variable separable, you are separating all the variables to their differential. All the variables that contain y should go to differential y. All the variables that contain x should go to differential x. We can now integrate both sides. We can integrate both sides. For the last case, we have dy over dx equal to the function of y all over the function of x. We can take this guy here and take this one to meet. We can take this one downward. So we have dy all over b of y. This one has come here. Then dx all over h of x. Now because the function of x is with differential x and the function of y is with differential y, we can now confidently integrate both sides. So these are the three possible cases of variable separable. Let's do some examples. Example 1. Let's do some examples. Suppose we have dy over dx equals to xy. As easy as this. Dy over dx equals to xy. How do we get the solution to this differential equation? How do we get the solution to this differential equation? This is just like case 2. Now the first thing, you will take the y to differential y and you take differential x to x. So if I divide both sides by y, I will have dy over y equals to, this will come to this side, we have x dx. So I can now integrate both sides. If you integrate 1 over y, you obtain ln y. And if you integrate x, you have x squared over 2 plus a. Now this is already a solution to the differential equation. So let me make y the subject formula. We can say y is equals to exponential x squared over 2 plus a. Now I can still bring your normal rule of indices says that anytime you have something like a raised to power b plus c, you can separate them to be a raised to power b dot times a raised to power c. So I can separate these two. This becomes y equals to exponential x squared over 2 times exponential a. Now a is a constant and the exponential a will also be a constant. So if we have c as a constant, 2 times c will still be a constant. If you have b as a constant, 2 times b will be a constant. If you have a as a constant, exponential a is also a constant. So anything multiplied with to a constant will give you a constant. Anything divided by a constant will still be a constant. Anything raised to the power of a constant is still a constant. A constant raised to power any other value is a constant. Constant times constant is a constant. So long you have constant and there's no variable, it will always give you a constant. So exponential a is a constant. Let's say b, let b equals to exponential a. So the solution to this differential equation, this is called the solution. We call b exponential x squared over 2. This is the solution to this differential equation. Now we said in our second video, I think, we differentiated this. If you have the solution, we can take it back to this form. We can still test it from this case. We can still test it here. How to get this to this form. You will observe that you can solve this back to this form. Let's do example 2. Let's say you have dy over dx and you have x squared plus 1. Let's say you have x squared plus 1, then you have dy over dx equals to y squared plus 1. Now this x squared plus 1 is a function of x. This full y squared plus 1 is a function of y. So the best thing to do is to take this function of y to this differential y, then take this function of x to this differential x. So if I take this one downward, I will have x squared plus 1 dy is equals to y squared plus 1 dx. I took dx to the other side. Now, this dx is supposed to have a function of x so that we can use variable separable to solve it. Now, we have to take this function of y to differential y and take this function of x to differential x so that we have dy over y squared plus 1 is equals to dx over x squared plus 1. Now, because it's already in this form, we can now integrate both sides. Remember, when you integrate y squared plus 1, you have tan inverse of y. When you integrate this, you have tan inverse of x, then plus your constant. So that's your constant. You can decide to leave it in this form, or you can expand. You can take tan of both sides. Y becomes tan of tan inverse x plus a. So you can open this bracket. You can simplify this. Remember from trigonometry that tan a plus b is the same as tan a plus, let me just write it here. Remember from your basic trigonometry that tan a plus b is equals to tan a plus tan b all over 1 minus tan a tan b. So I can simplify this. I'll have y is equals to tan inverse of x plus tan a all over 1 minus tan inverse of x, then times tan a. This will be our y. Now, tan inverse of x is x. When you have sine inverse of x, you have sine inverse of x. and you take sine inverse of x, you will get x. Because if you have sine 30, it is 0.5. So 30 is sine inverse of 0.5. When you take sine inverse of 0.5, you get 0.5. So the tangent of tan inverse of x is x. So y is equals to x plus, remember that tan A is also a constant because A is a constant. So the tangent of a constant is also a constant. Let's call it B. All over, we have 1 minus bx. So we can leave our equation like this. Don't forget, these two constants are the same. So if you want to obtain the differential equation from this solution, there will be no need for you to differentiate twice because we have just one arbitrary constant, which is b. Suppose that this place was b square. It is still one arbitrary constant, which is b and b square. B and b square. So in this case, this is the solution to the differential equation, to this differential equation. This is the solution to differential equation. Let's do one more example and that will be all for this video. One more example and that will be all for this video. Let's say you have dy over dx, 2x dy over dx plus let's say dy over dx is equal to exponential y. Let's say you have 2x dy over dx plus dy over dx equals to exponential y. Now, first of all, the first thing that is common here is 2y is dy over dx, dy over dx. So if I bring that out, I'll have dy over dx, open bracket, we are left with 2x plus we are left with 1 equals to exponential y. This is a function of y and this is a function of x. So let me first of all take this to this side. I will have dy bracket 2x plus 1 equals to exponential y dx. Now I have to take this function of y to this differential y and take this function of x to differential x. So we have dy all over exponential y equals to dx all over 2x plus 1. Now I can integrate both sides, or let me take this back to this form, equals to dx all over 2x plus 1. Now I can integrate both sides. If I integrate this is exponential y all over minus 1. If I integrate this, I can manipulate the top. Since I know if I differentiate the bottom, I will have, or let me just say let u equals to 2x plus 1. Du is equals to 2 dx. Du is equals to 2 dx. So what will be dx? So your dx is equals to 2 du over 2. So anywhere I see du, dx, I'll put du over 2. We have exponential minus y all over minus 1 is equals to integral dx is du over 2. Then 1 over, what is our 2x plus 1? U. So this is minus exponential minus y equals to, if you integrate ln, you have, if you integrate 1 over u, you have ln u dot over 2, then plus your constant a. Remember that u is 2x plus 1. So we have minus exponential minus y equals to ln 2x plus 1 all over 2 plus a. This is the same thing as exponential minus y equals to minus ln 2x plus 1 all over 2, then minus a. If I say let minus a equals b, because a is a constant and minus a will also be a constant. So let's call the other constant b. So this becomes exponential minus y equals to b minus ln 2x plus 1. raised over 2. You can decide to leave your answer like this, or you can leave it in different form. If I take this thing, this is simple ln square root of 2x plus 1. I can leave it in this form. If you don't like it in this form, you can also change. You can say let b equals to ln c, because the natural log of c is also a constant. So you can say this is exponential minus y equals to ln c minus ln root 2x plus 1. Now the reason why I'm doing it that way is because I want to join the two parts of the equation. Now remember from your rules of logarithm that when you have log c minus log this is the same thing as log c divided by this. So we'll have exponential minus y is equals to ln c over root 2x plus 1. So you can leave your answer like this, or you can still go forward again and take the natural log of both sides. If you take the natural log of both sides, you have ln exponential y equals to ln c over root 2x plus 1. So this is minus y ln e. Ln e is just 1. So you have y is equals to minus y is equals to ln this